Well, this is a pleasure to be here. But before I start, I want to acknowledge that the three of us wouldn't be here at all if it weren't for people who are in the LIGO laboratory, in the LIGO scientific collaboration, and in the Virgo collaboration and the Virgo experiment. And since some of you are here, I'm going to insist that you stand up. Would you please do that? They're really the reason we're here. Now, the three of us are going to give a talk which on the surface looks the same. You saw the titles, LIGO and Gravitational Waves. And I'll give you a little preview, and we won't really be able to hold to this preview exactly. I'll talk about the old times. I'm the oldest. And Barry will talk about the present, and Kip will talk about the future. Now, it's not going to go quite that way, and we will intermingle the times, so don't forgive us. But that's the basic structure. So let me start by those of you who don't really know much about gravitational waves and gravity. This is mostly a little bit of a pedagogical thing in the beginning. As most of you were trained in high school and possibly in college, is you learned about Newton's theory of gravity, which is a theory in which there are forces between masses, and that force gets smaller the bigger the distance between the masses. And it is a wonderful theory. It does almost all you need. In fact, it got the space program working. There's nothing terribly wrong with that theory, but it isn't right. Okay? And Einstein saw this pretty quickly. After he developed the special theory of relativity, it doesn't have a way in it of dealing with very large masses moving at high velocities. That's not in Newton's theory at all. And nor does it have a way of communicating information in the gravitational field from one place to the other. For example, if the sun disappeared, and we know it takes about 9 minutes for us to see that, it also should take something like 9 minutes for us to find out gravitationally that something has happened to it. And that's something that, again, was not in the Newton theory. And so this picture, which is hardly complete, but is some way to imagine this new theory that Einstein developed, is if you imagine a jungle gym, a big assembly that you played in as kids in New York, where I was, there were lots of those, and you take a cut through it, and you have laid out all those bars, and you've done one more thing, which isn't something you did when you were a kid. You laid clocks out on every intersection point. All along here, you put clocks everywhere. And what the Einstein theory says is what this picture is trying to show. If you take a cut through it, there will be, when you're far away from the sun, that's the sun, and when you're far away from the earth, when you're far away from those, let's say out here, space itself looks very Euclidean. It looks the same way as the jungle gym did. And the clocks that are running on all those intersection points, they all read the same time. But as you walk toward the sun in this plane, you'll notice that the distortion in space. You don't see the distortion in time because I didn't put you clocks there, but the clocks in here are running a little more slowly than the clocks out there. And a little bit of that also happens at the Earth. There's a little dimple that the Earth does. And the way John Wheeler explained Einstein's theory, he says, matter distorts space and time, and then matter moves because of the distortion in space and time. And that's the best I can do for you. Kip will do better, okay? And in that theory, there is also gravitational waves. And I want to show you first the gravitational wave. The gravitational waves move at the speed of light. You've heard that already. But they are, as you'll see in a minute, and what this picture will show, is they're a transverse wave. They're a wave that distorts space perpendicular to the direction in which the wave moves. And so let me turn on this little animation. But before I do that, because you'll get sick looking at it, there you are right there. That's you in that little red square. And now I'll turn on this animation so you can see the wave coming by you. And you'll see some patterns in this which are important for understanding how we detected these things. First of all, you'll notice that in, let's say, the horizontal direction, let's say it's expanding, but in the vertical direction, it's contracting. Now, any one moment, these things will flip, but they will be opposite motions vertically and horizontally. That's one thing. So that's a pattern that you exploit. By the way, you'll see how we exploit that. The other thing about it is that these are objects that you threw out into the space as the gravitational wave comes through. I should have told you that. So you look here, near you, let's say these little masses, they don't move very much. But the masses that are far away from you, they move a lot. And that's a picture of a constant strain along, at any one moment, the change in distance between objects is proportional to their separation. And that change in distance divided by the separation is called the strain. And we will talk about that a lot. That's the quantity we measure. Well, we actually measure the distance separations, but the quantity you describe as the field quantity in the theory is the strain. And so let me tell you a little bit of history now. We talked already about this theory being developed about 100 years ago. In 1915, Einstein gave the world the general theory of relativity, which was described somewhat by that first picture. But then, in 1916, he wrote a paper, and I have to drink something, just to bear with me. It's not forever. Yeah, what happens is that in that theory, later on he had a paper in 1916 where he describes a lot of things that showed that it had a Newtonian limit. And he also shows that there are gravitational waves in that 1916 paper. And the only reason why I bring this up here is because of a very interesting statement he made at the very end of the paper. He's described these things, and I'll talk to them about them in a minute, but he describes an equation which is up here. I will only tell you what that is. It says this is the strength of gravitational waves, and this is the source of gravitational waves, the oscillations and accelerations of matter. And he says something extremely interesting. I have it here in German, but I'll read it to you in English. In any case one can think of, A, that quantity will have a practically vanishing value. This is at the end of that paper. It says you'll never be able to measure this. It's of no consequence to science. That's effectively what he was saying. And so he makes a mistake in this paper, but that has nothing to do with it. In 1918, he corrects that. But I'll be presumptive a little bit, and I've asked the people who will have the Einstein papers to try to find what I'm about to show you. And they haven't found this on the back of an envelope or in his notebooks. But I'm sure it's there somewhere. So I'm trying to give you a little feel for why he made that statement. And you have to put yourself in the context of 1915, 1916. What did people know about, and what did they have? And the first thing Einstein might have thought about is two trains colliding. How much gravitational waves come out of that? And so let me give you, this is not, it's only formula, but I'll explain it to you, okay? So here's the strain, that's H. And this is the quantity that when you want to estimate how much strain you get from some kind of motion, it's a very simple estimation formula. It has the Newtonian constant in it, the mass of the objects, and the distance you're away from them, and the velocity of light squared. That quantity, gm divided by rc squared, is a very important dimensionless quantity that we all know and love. What it is, on the Earth right here, it's about 10 to the minus 10. It's very small. You live in an extremely small gravitational field, even though you may have to have knee operations, okay? But on the other hand, what you'll hear about from Barry and Kip is places where this number is closer to 1. It's huge. And those are places where around black holes and other places, the beginning of the universe, and so forth. And the other quantity is v squared over c squared. This sort of a measure of how much motion there is. And that's velocity divided the velocity of the objects divided by the velocity of light squared. So that quantity allows you to estimate h. So here, for example, for the two trains coming together, and by the way, trains in the United States don't go much faster than this nowadays. That has not been much advance in that. Maybe in Europe, but not here. Not in the United States. So let's pick 10 to the 5 kilograms for the mass, the velocity about 100 kilometers per hour, a collision time of a third of a second or so. Yeah, and you have to be far enough away so you're not looking at Newtonian, just a new induced field. You have to go far away enough so that you're looking at the radiation field, the field that carries these waves. So you have to go out a wavelength about, that's 300 kilometers. And the h value you get is 10 to the minus 42. And that is truly impossible. We can't even do that now. And that's why Einstein probably made that statement. So he might have very well looked at something else. I mean, he knew about stars, and he knew about binary stars. And these people, he did not know about the galaxy. The galaxy was something that was being discovered at the time. And so, but suppose he put numbers into that. And he takes stars that are going around each other once a day, near the two stars. And suppose they're at a distance of about 10,000 light years away. He might have guessed at that. It might have been 30. He probably didn't know exact number for the size of the galaxy because he really didn't know about it. And you get an H value, which isn't pretty small. It's 10 to the minus 23, with a period of half a day. Every half a day, half a period. Every half day, you go through a thing that looks the same. So you look for gravitational waves with a period of half a day, with a strength of 10 to the minus 23. That's what we would do now. But in his day, he would have said, well, how much energy is being taken away by gravitational waves? I'm not going to describe that formula, but if you look at it, that's what that gives. And you would get something like the following. I'll just say what the end result is here. You would have gotten that it would take 10 to the 13 years, 10 to the 13 years, for those stars in a telescope to look like they were changing their distance, their separation. It's clearly hopeless. And so, in both ways, as an astronomical thing and as a technical thing, I can completely understand Einstein. Now, it turns out in our epoch, finally, there was a situation where that experiment that I just described to you, or the measurement I just described to you, was actually done. But was done fairly trickily. And this is sort of the 100 years later, the technology has changed, and what we know about astronomy has changed. And this all becomes possible. And the thing is, these are Nobel Prize winners, these two. This is Russell Hulse, who was a graduate student at the time, and Joe Taylor, and they both were at the University of Massachusetts at the time. They went to Princeton because this was a major discovery, and they got scooped up by all these wonderful places. And what they discovered was a system of, they didn't know it, but they discovered a pulsar. They were looking with a radio telescope. They looked, and they used the Arecibo telescope, in fact, the one that got into trouble in the big hurricane. And they listened, and they heard a thing going brrr like that. And it was going at about 17 times a second. That's a pulsar. And these are neutron stars, stars made completely of neutrons. And they have the mass of the sun, and they're about the size of Stockholm. It's really unbelievably dense thing. And what they heard is the pulses coming from that, but they weren't going at a regular rate. Sometimes they were going a little faster, sometimes they were going a little slower. And it turns out when they mapped this, they kept looking at it, they found that for about 4 hours, and this is the model of it, it turns out to be a pair of neutron stars, and they're going around each other, and when this pulsar, which is sending its pulses to the radio telescope, is moving toward the Earth, which is over here, it goes a little faster, like from the Doppler effect, and when it's moving away from the Earth, it goes a little slower, and that's what they saw. And they mapped that, and they watched it for many, many years. This is time over here. And they saw it in 1973, and they kept watching it. And what they noticed is all the wonderful tests of general relativity were done by that system. But the one that was most telling and most interesting for us today is this one. It's the one where they plot the length of time it takes for the orbit to complete. Every time you go around once, it's the period of the orbit. And it's being plotted here. This is in time, epoch of watching the system. And this is the period of the orbit getting shorter and shorter and shorter. These are minus signs over here. And the dots that are in here are their measurements. And the line that goes through them is the prediction from the 1918 paper with a factor of 2 correction that Einstein made of how that system should lose energy due to gravitational waves. So that was the very first indirect measurement, but the first measurement of gravitational waves. A really profound thing, and it won a Nobel Prize. Okay, so then the next thing that happened, and this is again, it happened because of technology changes. And what happened, people began to have the fact that you could think of these very small strains, and you now had equipment, as the technology changed, where you could think of making a measurement. And the first person who actually thought of that was Joe Weber. He's right here. He was a professor at the University of Maryland. That's him. And there he is with his invention. The invention was, by the way, also an invention made together with John Wheeler, who was Chip's thesis supervisor. Okay? And what it is a great big bar. It's like a, well, you can see how big it is. It's as big as the man, maybe bigger. And what Joe was hoping will happen is that a gravitational wave will go through this thing, stretch it momentarily, and leave it singing, much like you hit it with a hammer. And there he is attaching little strain gauges to the device so he can hear that with the electronic equipment that was becoming available. And what happened is, to his misfortune, he saw something. And in fact, he saw something. He made several of these and put them in different places in the United States. He invented the idea of using coincidence methods to do this. And he had a system like this in Chicago, the middle of the United States, one in Maryland, and another 8 miles away from his office in a golf course in Maryland also. And he saw coincident pulses. And in 1969, he published a paper which said he had discovered gravitational waves. And it turns out that many, many other people became interested in doing that. In science, that's what always happens. A stunning result like this can be tested by everybody else. And to his misfortune, nobody else saw these waves. Nobody else saw these pulses. And now we know why people didn't see the pulses. The strength, we'll talk, and this is something useful to remember, the strength that you need. And he was able to measure with these things a strain of about 10 to the minus 15. 6 orders of magnitude, bigger than what ultimately you needed. Okay, I'm sorry, okay. I didn't realize that was happening. So, what happened is people began to think of other methods of doing this. And one method of doing it, I'll describe here, is not with a bar, but rather with a thing which really, in the end, was more successful in making the real measurements. And that is to look at free masses, but like that picture of the gravitational wave. A mass over here, and you put another mass over there, a goodly distance away, and you take and measure the time it takes. You want to measure their separation as changing as the gravitational wave comes by. That same picture of all those dots that I showed you. And so the idea is really simple. You take and have a light, send it, put a clock on those, put clocks on the masses, or actually, let's start that way. Clock here, clock there on those masses. Send light, measure the moment when the light left this mass, and find out with another clock over here the time when it hits that mass. That's a way of measuring the distance between those two masses. And then let the thing unfold, and as the gravitational wave comes along, it'll change that time because it's changing that distance. It's as simple as that. Now, if here's the idea, and this is a way which actually almost works. Here you have a laser and a beam splitter, which is a device that splits the light. And that's in the picture I showed you. That would be the red square that I showed you. Here is a distant mass, and that's a mirror. And there's another distant mass. And remember, the gravitational wave is coming down. And what it'll do is it'll stretch one of these and compress this, and it'll flip. Then this one will stretch, and that one will compress. And here is the way you make that measurement, which is effectively timing light. So what I'll describe as it goes along, where it's red is light. And we're thinking of red lasers when they made this picture. But what you see is the waves. These are the actual waves inside the power of the light. And where it's red is where there's light. If you do it right and make the time here equal to the time of light there, you get no light going to the photodetector. That's the idea. And so we'll show that's where the photodetector. Now when you move these masses, one out, the other one in, you'll see that there is light when the motion makes it so the path lengths are no longer equal. And that is, in fact, the basis for the entire experiment. It's no more complicated than that. The big problem comes, you have to do it extremely well. And here is how well. Kip comes on the scene. I met Kip in 1975 when he and I met in Washington, D.C. He was thinking at that time, he was giving testimony to a committee, and he and I spent the night talking about what kind of experiments are interesting to do. And he was at that time, had already the most successful group, I think, in the country doing theoretical gravitation. And he was hoping to start a group, or have Caltech start a group in experimental work. And what we came on is that Kip, at that meeting, he and I talked about that ultimately this technique that we were just talking about here would be a good thing for Caltech to work on. But he told us something then already, that you couldn't just do it in this haphazard way, that it had to be done. And he was one of the first to tell us that if you want to get into business, you had to measure h's, or these strains, delta changes in length, divided by the length of 10 to the minus 21. I think this is Kip about that time. He'll tell us if I'm wrong. Yeah, he's agreeing, okay. And what the big thing is that if you make something, and now we're getting on mixing times, but that's too bad. Suppose if you go to something as long as 4 kilometers, and you do the little bit of arithmetic that's associated with that, you find out that you have to measure distances at the ends, that motion, of 10 to the minus 18 meters. That's something like 1,000th the size of a nucleus of an atom. That's very hard. And here is the challenge that this threw at us. If you want to use light to make that measurement, light has a wavelength of about 10 to the minus 6 meters. You have to go 1,000,000 times a million times a million, more sensitive than the wavelength of light to get into business. That's what he was telling us. If you want to use light to do this. But then you had another problem, which in the end turned out to be much harder than that problem. And that is, even though you might have made a wonderful method of measuring things, their position with light, the things that you're looking at are not going to be standing still well. They're going to be kicked around by everything in the world, especially the world. And because you and I are sitting right here where we're being jiggled around by the ground by about 1 micron, at least a few microns. So 10 to the minus 6. So you got another factor of 1,000,000 times a million. And that one was a really hard one. And so here is the things that went on, and now the rest of this is really about people. Because people are critical to getting that factor of 1 billion and 1 billion. Billion, let's say, well, European billion. 10 to the 6 times 10 to the 6. So, a guy who really helped a lot in this thing was a guy named, who was not so heralded, it's a man named Pirani, who was a theorist, who told us, yes, it was possible to measure gravitational waves with things freely floating around. That was a big, big challenge. There was a lot of worry about whether you could ever extract any kind of measurable signal from gravitational waves. And he showed us that there was an invariant way, didn't depend on the coordinates that you used, of showing that a gravitational wave was moving the masses, changing the space. And that's, of course, exploited in this. And several ideas, and these are all people who were critical to it. Some of the gimmicks, some of the tricks that you need, and some of the tricks were first exploited in a small prototype at MIT, but it was not a very good prototype. But the idea is, I won't describe that picture anymore to say the following thing. We knew already that you had to use lasers. You couldn't use just a very weak light source. The other thing you needed to is you somehow had to make the light go more than once back and forth. You had to bounce the light back and forth. And you had to do tricks to get around the noise. And there were tricks you had to modulate the light. You had to use all the cunning tricks. And the other thing you had to do is you couldn't put the masses right on the ground. You had to somehow float them so the ground motion would not make a signal so large that you couldn't see the gravitational waves. And all those tricks were tried in this prototype. But the people who really did it right and who actually demonstrated to all of us that this was possible was the group that's up on top here. And you'll notice that this is the group that was in Garching and Max Planck group. And here is Heinz Billings. He was a guy who worked on bars with Weber, was severely disappointed. The whole group, after they did it, they were one of the first and most accurate to show that Weber's experiments were not right. And so they were fishing around what would be the next thing to do. And instead of quitting, they decided they were going to go into this interferometric method of doing this. And here they are, and each one of them, the one who's in the room here is Albrecht Rüdiger. He's somewhere in this room. I haven't seen him. But unfortunately, most of them are dead. Walter Winkler is still alive. And Frau Schnupp, and we have celebrated her. Her name is now ingrained in the apparatuses we have for a particular trick of making it so you can see the fringes better. Maischberger was deeply involved in the hanging all the masses, not just the mirrors, hanging everything. We didn't think of that. Just hang everything. You have to hell with it. You just learn how to do interferometry with things that are on suspensions. Forget about it, how difficult it is. And the same thing with Rüdiger. He was also advocating that. And here's Roland Schilling, who invented all sorts of ideas of how to get toward that factor of 10 to the 12 in sensitivity. he also invented, along with Ron Drever, who we'll talk about in a minute, the idea of power recycling. So then there was another group. So they were, what did they do? We'll talk about a little more, but they built a 3-meter prototype, much faster than the people at MIT did. And they showed that a lot of the ideas were right. They also showed that a lot of the thinking that had been done ahead of that had mistakes in it, that we hadn't thought it through properly, which was very important, especially the scattering, light scattering. That's something they discovered. Well, here's the other group that was very important in this development. This is the group at Glasgow. And here's Ron Drever. Ron Drever was then later came to Caltech and worked there, and we'll talk a little about that in a minute. But Jim Huff was his student, and here's Brian Mears invented a very critical idea that has now become important in these interferometers. We'll get to that in a minute, but to add another mirror in a very unlikely place. And Harry Ward developed the ideas of how one might align systems like this. And that group was all at the beginning. They invented a whole bunch of new ideas also. And that group was critical in this business of going to the 10 to the 12 in the position sensitivity. And the things that actually then followed this were instruments. More prototypes were built. Caltech, when Ron Drever went to Caltech and Stan Whitcomb was hired, what happened, they built this instrument. I wish I had more pictures of it and more of the pictures of people, but they built this 40-meter instrument. And that's still operating. That 40-meter instrument was a test bed for the things that went into the LIGO, into the actual LIGO. And here is the other experiment that was done by the German group. And the German group with David Shoemaker, who had an import from the United States at the time. And they built a 30, after they got done with their 3-meter prototype, they built a 30-meter prototype and showed that the scaling laws worked. That was absolutely critical. And they then, in fact, make a lovely statement in here. At the end, you can't read this, but I'll tell you, they got past the sensitivity of the bars, the best bars. They did better with this instrument than you could do with Weber bars. And that was an extremely important statement because that made everybody say, aha, this is the wave of the future. And if you're now going to build something big, you're going to have to do it with something that's going to detect this kind of thing. Here's the group at MIT a little later. The reason why I like this is because it has some of the people who are now leaders of this thing. They were young people. There's Nergis Mavavala, and then there's Peter Fritschel right there. And in the back is Brian Lance. And this is Mike Zucker, who was at Caltech working on the 40-meter. He came to MIT. This was, after a while, it turned out those two groups became sort of completely interchangeable. And that was, a lot of things were done there. I won't go into all of them. All preparatory to what I'm about to show you. So, this is out of time, Sirens. It should really belong in Barry's talk, but I have to show it because he wants to show other things too. This is actually the interferometer that actually made the detection. And I'm not going to walk you through except to show you where some of the things you already know exist. Here's the laser again. There's the beam splitter. Here's that distant mirror, and there's that distant mirror. Here's the gravitational wave coming down. The things that have been added to it are these two masses, this one and that make it so that this becomes something called a Fabry-Perot cavity. It's a way, effectively, of bouncing the light back and forth about 300 times. And in here, about 300 times. And then here is the photodetector. And again, you operate it in such a manner that no light goes to the photodetector when there's no gravitational wave. And then here's the idea that both Ron Drever and Schilling had. You put another mirror, which you haven't seen before, between the laser and the beam splitter. And what that mirror does, I will just describe what it does, and I'll show you, is it takes the light that isn't going to the photodetector, that comes out of the laser, goes into the interferometer, is not going to the photodetector. It would normally go back to the laser, but you make it so you bounce it back into the interferometer and build up the light inside the interferometer for that reason. And that makes it as though you had a very much more powerful laser. A very clever idea. Then, here's Brian Mears' idea. And that is that you put another mirror, which is not, this is not immediately something that everybody can capture because you need to know a lot more than I told you why this works so well. But what does it do? By putting a mirror between the detector and the beam splitter, it makes it so you can tailor the response of the interferometer. You can make it have different shapes. make it have so that it's more sensitive at certain frequencies and stuff like that. And this is called a power recycling mirror, and that's called a signal recycling mirror. And that's an important part of advanced LIGO. So this is the advanced LIGO detector. Okay. Now, that's the technology of the how do you make the light get that factor of 10 to the 12. We're not quite done with the technology of how you make the ground motion small enough. But first, let's talk about how you begin to build up the idea that you don't want to do just prototypes. You would like to actually build a detector. And that happened in about 1980. That we began to think hard about how might you build a system that actually could detect something. And we were driven to that for many, many reasons. It was hard for students, at least at MIT, to keep working on something which didn't have a physics result, had only an engineering result. And I don't know, at Caltech it was different. They had a different attitude about this. But the thing is that what we began to think about is really we asked the NSF if we could do, and we were also encouraged by the NSF, and we'll get to that at the very end, to make an industrial study with industry to find out where could you place a thing that was big enough, and we thought of 5-kilometer arms, maybe even 10-kilometer arms, and could you get the lasers, and how would you make the vacuum system, and all the stuff that goes on that if you want to convert a thing on a tabletop into something very big. And there was a study done, and there are two people here who were quite central to this. Peter Salson, who helped in that. He was a postdoc who had come from Princeton. And Stan Whitcomb, who had been brought on by Caltech, and he wanted to be part of this same study, and this is called the Blue Book study. And it did that. A little bit later, and with very significant differences, because during that time, between 1983 and 1989, we did a bad thing. We had Ron Drever and Ray Weiss trying to run a big project with the help of Kip Thorne. That was hopeless. And it was noticed by a committee that met in 1986 that had been asked to look at this whole field. And that committee had been started by Richard Garwin, a very significant personage in American science, who said, look, if you're going to persist with this, you better have a summer study. And that summer study said, look, it's a wonderful experiment. Don't hold back. Build 2 of them. Make them the long length. They said everything right. And they said, you can't do it with that crazy bunch who are running it. Okay? And said, get yourself a director. So we got a director. And that director was Robbie Vogt. And Robbie Vogt guided us through writing a proposal, which was really a textbook. It's a beautiful proposal. It cost us a lot of time. It's a first real document that showed a lot of the techniques and how it might build this and costed it properly. And what happened is that proposal became a joint proposal of Caltech and MIT. And there's one very elegant thing that Robbie Vogt did, among others. He did something which was he coupled, in the process of thinking about this project, he coupled an engineer, if we had an engineer, and we didn't have enough of them. And Barry later, when he took this over, realized that. But we had some engineers. But we had a lot of scientists. And the idea was, couple an engineer who knew how to count money, but also knew what was practical, with a mad scientist who wanted to make sure you didn't compromise the experiment, and couple them together so that they designed something and estimated something which was going to be both realistic as well as able to do the experiment. And that was a very good experience. I can show you only some of the people here who did this. And so well, you recognize some. There's Ron, there's Kip, and then there's a chief engineer at the time, Bill Althaus. Here's an engineer who stayed with the project. I couldn't get a picture of the vacuum engineer at the time who was doing this, and that is Bowd Moore. And here's Larry Jones, and Larry Jones was tagged with me, and we helped design the big beam tubes and so forth. And so this was a very important moment in the history of LIGO. Let me go quickly more back to the science a little bit, or the technology. And that is, this is the kind of thing that evolved when in that proposal, we want to show people what limited the performance of a gravitational wave detector. This is, in fact, a plot of the things that limited the first detector. Barry will show you the evolution of that detector. But I just want to walk you through some of the things in here which are still important. What this is frequency. In other words, this 1 hertz, 100 hertz, that's an important region, 10 kilohertz over here. Here is a strain of about 10 to the minus 23 per bandwidth. I'm sorry, this is here you're using spectra. So if you want to go back to what I was telling you, you have to multiply this number by the square root of the frequency. That's a detail for those of you who want to follow. But that's not important. What I want to show you is what was limiting this detector. At high frequencies, it's this line, and that's the amount of light power you had. At low frequencies, it was limited by something else, but I want to continue this because this is important for Kip's talk. This is part of what's called the quantum limit. The amount of light you use to tell the position of the mass is, if you use more light here, having more photons, you can bring that down. But you pay a price for that. Over here is another piece of that same noise, which is called the radiation pressure. And that is, if you use more light, you push on the masses, and there's noise in that light that pushes the masses around. And many of you who have had quantum mechanics know that there's something called the Heisenberg Microscope. This is just the Heisenberg Microscope macroscopic, okay? When you try to measure better the position of something, you impart more noise momentum to it. And that's what this curve says. And this is something we're now battling, and you'll hear more about that from Kip and from Barry. The other noises in this thing are, for example, how well can you get rid of the ground noise? And at the time when we were designing this limit is the noise that shakes the ground, the seismic noise, and that makes a limit at low frequencies. And then this limit is the fact that everything is room temperature. And when everything is at room temperature, every surface is shaking due to phonons, so the sound waves. In the sound waves that are generated by just the fact that there's energy in the heat. So that's thermal noise. And here are some things that still plague us. Here is the thing that made it cost so much money. If you had a vacuum that was only as good as a certain value, this is a value that you could get moderately easily, that would be a limit for a detector that would be better than this. And I have failed to tell you something. That proposal in 1989 proposed a 2-stage procedure. It's proposed we build one that we know how to build now, or almost know how to build now, and another one we hope to build in the future. And that would need much better vacuum than this, in fact, down here. And getting that whole assembly together, making the vacuum good enough, was an expensive proposition, but we succeeded with that in a very unique and interesting way. And so what remains as a noise is this one right here. This is very important noise. And that's the last thing I'll show you in this picture. You'll notice it gets worse and worse and worse the lower the frequency. And that is a noise which we have to contend with. And it's the noise that we will have to continue to contend with. There are 2 noises in this we have to continue to contend with. This is one of them, and the other one is the one I already told you about, which is the quantum noise. But this one is something which is not easily thought about always by people. You have the ground shaking, and that's fine. But when the ground shakes, there's another piece associated with that. A wave traveling in the ground causes the density of the ground to change. And let's say this bunch of flowers is the mirror. And here are these waves coming by. And as it moves, here's this compression going on in the ground like that. And as the compression goes by this, it's a little higher density over here. That pulls the flowers over to the ground. That's a force on the mirror. That's plain Newtonian gravity. And that's the noise. The waves are there, the acceleration there, but the density changes in the ground make a change in the force on the mirror. And we have to contend with that. And also the density changes in the atmosphere. And there's the Hungarian group that has joined LIGO has thought about methods of measuring the barometric pressure carefully enough so that you can measure that. So those are noises that are still with us. And we have to learn how to get around them. And that's one of the reasons why people propose the LISA experiment, which Kip will talk, Kip will talk about. So, all right, that's sort of a little quick guide through all the things that contaminate the gravitational wave signal. The last thing I want to quickly say, and this is really in Barry's part of this presentation, is what we did to make the final steps in getting rid of the ground noise. Not the gravity gradient noise, but just the acceleration. And this was a contribution to LIGO, for advanced LIGO, done by the group in Scotland. And this is a very elegant suspension. Here's a spring that's attached to the ground, and there's a mass. And this is a suspension. And if you wiggle a suspension quickly, the thing you hang it from doesn't move. So you do that once, then you do it once again, You do it once again, you do it 4 times, and here's that very precious mirror that's going to be reflecting the light. And that 4-stage suspension is a critical part of LIGO, and especially a critical part that we made a detection. But even more important, as far as I'm concerned, is this thing, which is much too complicated to tell you about, but I'll tell you what it does. It's an active system that gets rid of the ground noise. And you have a lot of experience with that in your hearing. I don't know how many of you use these noise-canceling headphones. I'm sure that people here, yeah, okay. It's the same principle. What you do is you put a very sensitive seismometer on a platform and measure the motion of the platform, and then what you do is you push on that platform to get rid of the signal in the seismometer. That's the same thing you do with the headphones. That the headphones listen to the sounds that are coming in. They generate a sound that's the opposite sign in the headphones, and you don't hear the outside world. You only hear the music that's on the other part of the headphone. That's how that works. It's the same idea. It's an active system, and that is absolutely critical to us. And that was developed both by LIGO and Stanford University. Okay, now people again. I want to give a special credit to Richard Isaacson, who is in the audience, and I know he's going to be shirking when his name is mentioned, but I want to tell you what he did for us. First of all, he was a first-class scientist in this business to begin with. And he wrote a paper quite early in the 60s where he showed a thing that was very controversial at the time, that gravitational waves actually carried energy away from a source. That was heavily debated. A lot of people thought it was just a coordinate problem, but he showed there was actually energy leaving a gravitational wave source. And here he is. And what he did, he became the discipline chief for gravity at the NSF. And he convinced his boss, Marcel Barden, that this crazy idea that we all had really had merit. And he did it at a time when it was not so easy to do that. We didn't have the technology in hand, and we didn't know what sources we were going to see. And he had to sell this idea to his boss. And he did a magnificent job of it. Then he sold the whole agency on this. Okay? And that's something which is spectacular. Without him, this would not have worked. And these are some of the people who were influenced by that. And I want to say something special about these are directors of the NSF, which were critical to our development. Rich Isaacson was actually deeply mixed up with Eric Bloch, with his boss, and Eric Bloch was an engineer. And the same thing happened at MIT. The engineers were the first to recognize, and then at MIT, that this might have some value. The electrical engineers around me. It wasn't so much the physicists. And so he had the idea that this was exactly the right thing for the NSF to get into. Something very risky, but had a tremendous payoff. And so Eric Bloch pushed it. And then when things really began to happen, and there were people who didn't like the idea that LIGO was beginning to use money from the NSF. There were people in the astronomy community that actually resisted it. You can read the newspapers as well as I. And Walter Massey, who was head at that time, a little later, actually told these people who were very influential, no, we're going to do this because it's the right thing for the country and it's the right thing for the NSF. And it was quite a struggle, and he was a magnificent person for doing that. And then, to make it all happen, the head of the NSF at that time, and this is in Barry's epic, was Neil Lane. And Neil Lane helped the NSF figure out how to go to Congress and say, look, the NSF needs a line item for big projects. It hadn't done big projects before, but that's what we need to do. And so there was something new invented, and that's how you get money. You don't go to Congress complaining. You never go to Congress complaining, stop this and give it to us. That's the wrong way to do it. What you do is, here is a good idea. Why don't you try to fund this? And the idea was, the NSF has all this science. We sometimes need to build big projects, and we need big chunks of money periodically. And that's still in the NSF budget line. And Neil Lane was absolutely critical in doing that. And now, last slide is, this is when the project, as far as I'm concerned, actually got started. Because then, enough people were brought in. Finally, we had somebody who understood that it took more than a skunk works to make things happen. Barry came. We were lucky that Barry came, partly because an unluck of the high-energy physicists, the superconducting supercollider got killed by, I think it was Clinton that killed it. And he brought Gary Sanders, who was in the audience, who was a project manager, who was a superb project manager. he then hired more people. Thank God. He hired Albert Lazzarini, who's also in the audience, and Dennis Coyne as a chief engineer. And he has been with the project for a long, long time. He's now doing something very interesting, different than this. And what's happened is that Stan Whitcomb was brought back from industry. It was already under Robbie, but he really was made and became sort of the chief scientist of LIGO. And I'm done. Thank you very much.
Okay, thank you very much. Yeah, you will have your chance to come up later also. Thank you.